So this week, oh, thanks guys. This week, we'll be hearing about LHC physics from two speakers, and then we'll also have a virtual tour that the kind people at CMS at CERN are going to come up. So first, I'm going to ask everybody, if you're not in the first 4 rows, to stand up and come into one of the first 4 rows so we can cluster forward. Please, please, thank you. And also everybody else stand up too so we can do breathing so that we can be present in the room. Okay. What? Moving forward. 2. And 3. Okay, thanks everybody. Thanks for doing that. Thanks for coming in here on this Saturday morning to learn about particle physics. Today we're going to start with Mike. Yeah. Okay, let's see. Set up with the... Have you used this before? Something. So Mike is a scientist here at Fermilab. He focuses on theoretical physics and aspects of lattice QCD as it relates to high energy particle physics, as well as neutrino interaction. Previously, Mike was a postdoctoral fellow at MIT before coming here. And this anything
No, that covers it.
And he's here to tell you today about the standard model. So good.
All right, thanks, Gray, for the nice intro. And thank you all so much for coming out here and spending your Saturday morning learning about particle physics. This is really awesome to see so many enthusiastic faces even at 9 in the morning on a Saturday. So I have the small charge of explaining the standard model of particle physics to all of you. So the main content of the standard model, to put it in one nutshell, is that almost everything that we observe in experiments can be described in terms of 4 fundamental forces. So you're probably most familiar with gravity. That's the force that keeps you stuck to the floor instead of flying off the Earth into space. Electromagnetism similarly provides the force that keeps electrons stuck to the nuclei of atoms instead of, again, flying off into space. And one of the fundamental features of electromagnetism, as the unified theory of electricity and magnetism is known, is that like charges repel, opposite charges attract. That's what lets the electron stick to the nucleus. On the other hand, the nucleus is made of protons that are all positive and neutrons that are neutral. So according to just electromagnetism, everything in the nucleus should be trying to repel itself from everything else, and the nucleus should be wildly unstable. The fact that it's not tells you that there's some additional force that's much stronger than electromagnetism that's responsible for keeping the protons and neutrons together in nuclei. Scientists try and keep names simple wherever possible, so this became known as the strong nuclear force. And it accounts for most observations of how nuclei bind, but there are other reactions that don't follow the rules of the strong nuclear force that led scientists to postulate the existence of an additional so-called weak nuclear force that's responsible for processes like a neutron decaying into a proton, an electron, and a nearly invisible particle called a neutrino. So the standard model is the collection of particles that are postulated to interact according to these forces. And there's specific rules written down in a mathematical framework called quantum field theory for how these particles and forces interact with each other. It also has about 20 parameters, things like the masses of the particles, that aren't predictions of the theory, but are things that you need to go out and measure, and then you can use the theory to predict other things. So before diving into the specifics of what these particles and interactions are, I want to step back for a moment and just talk about the process of building scientific models in general. And model building should always start with data. If you don't have any data to test your model, then you can make up whatever you want, and you'll have no idea whether it actually describes anything in reality. So once you have some data, you'll build some sort of model that has rules, usually written in math just because it's convenient, for how your system will evolve in time. These rules should ideally be simple enough to fit on a coffee cup, but as the complexity of your system grows, often the complexity of the rules that you need to describe it or the number of parameters grows. And these parameters come in two types. There's universal parameters like the electron mass that you just need to measure once and you're done. And then there's also system-dependent parameters. You could imagine if you're trying to build some model of fluids that the boiling point might be an important parameter, and that's something that you'll have to go out and measure separately for freshwater and saltwater and anything else you might be trying to describe. But once you have all the parameters you need to describe some system, then the process is to think of your model sort of like a hypothesis and make new observations that will test the predictions that you can make with your model. Either they're right, at which point you gain some confidence in your model, or they're wrong, at which point you know for sure that there is something wrong with your model, that it's either incorrect or incomplete in some way. You go back, fix or replace the things in your model you need for it to be able to describe the new data, and then rinse and repeat. And this iterative process of refining and testing models with data is really the heart of the scientific method. And the standard model of particle physics has emerged from 100 years of this process through particle physics experiments around the world. And so I want to take you on a tour of at least most of the particles in the standard model. And our story starts a little over 100 years ago, when scientists had just discovered electricity. And what was realized in the early 1900s is that shining a light source on a metal sometimes produces an electric current. And this is now known as the photoelectric effect. Your light source you can describe with two parameters. The frequency is basically just the color of the light. And then the intensity is a measure of how much energy your light source deposits per second. On the other side, if you're emitting some electrons, you describe them with the energy that they're carrying away and the number of electrons that you've emitted. And so the classical theory of light as a wave in the early 1900s makes some predictions in this language that the energy of the electrons that come out should be proportional to the intensity of the source that you shine on it. More energy in, more energy out. However, this theory had a problem in the early 1900s in that that's not actually what the experiments showed happened. And what the experimenters found is that there's absolutely no electrons emitted if the frequency is below some critical value, and then there are if it is. And there's also no time delay. You'd think if light was just a continuous medium, you'd eventually build up enough energy from a weak light source to emit an electron. That's not what happens either. There's no time delay. Electrons are either instantly emitted or not. Einstein then made a new theory in 1905 in which the energy of light was carried in these discrete packets. And the energy of each packet was proportional to the frequency of the light. And this theory was able to describe all of the data at the time. It is a model that you should think of as having two parameters. One of them is a universal constant of nature. That's the proportionality between the energy of the light and the frequency. And then the other is a system-dependent parameter that's sort of what's the threshold of energy for any given metal that you need to be able to start emitting electrons. And so this was able to capture all of the descriptions at the time. You have this threshold effect. Things happen instantly if they happen at all. And importantly, it also made a prediction. It predicted that above this critical value, the energy should grow linearly with the frequency, and the slope should be the same for all metals. So this should be pretty straightforward to test. And indeed, 10 years later, experiments by Millikan showed that you get this beautiful linear dependence of the emitted energy on the frequency, and even gave a value for this fundamental constant, now known as Planck's constant, that agrees pretty darn well with modern determinations. And so this gave us confidence that Einstein's model was actually onto something. It made predictions that were then validated. And 6 years later, Einstein got the Nobel Prize for this description of the photoelectric effect that had been validated by data. He then went on to become arguably more famous for his theory of relativity, the first version of which was also published in 1905. Good year for Einstein, but that took much longer to go on and be experimentally validated. So, of course, we now have much more evidence than just Millikan's experiments that light is made of photons. Things like night vision goggles and photomultiplier tubes and modern physics detectors rely completely on the photon nature of light in order to work. And similarly, things like solar panels and lasers really use Einstein's theory of light as a starting point. And the fact that all of these technologies work the way they do is a beautiful demonstration of the power of this model of light as little packets of photons. So in the subsequent 100 years, we've met a bunch of other particles. And some of them, it's important to admit, came as total surprises to the theorists. So about 20 years after this triumph of the photoelectric effect, experimenters like Anderson started putting cloud chambers at the tops of mountains. So these are sort of superheated gas chambers in the initial versions that if you have some high energy cosmic ray particle streaming in from space, will enter the detector and leave some track in it as it effectively boils the vapor that it's moving through. And if you put this thing in a magnet, now you'll get tracks whose curvature depends on the charge and the mass of the particle that's moving through it. And with this principle, Anderson and collaborators were able to detect electrons coming from outer space and cosmic rays. And they also had this beautiful picture, which in one shot proves the existence of antimatter. Because this cloud chamber is in a magnetic field in which an electron would curve this way to the right. And it would have exactly this same radius of curvature, but this track has the opposite sign. So what this proved is that there is some other particle out there that has the exact same mass as the electron, but opposite charge. And this is something that fit in nicely to the theories of relativistic quantum mechanics that theorists were developing at the time, but was just one bridge too crazy to really predict for the theorists before it was measured. Not long after that, the same suite of experiments discovered an additional particle that looked like the same charge of an electron, but 200 times heavier. And the famous quote for the discovery of the particle that we now call the muon is, "Who ordered that?" Because it could be accommodated into the existing theories, but there was absolutely no theoretical motivation at the time for the existence of the muon. People initially thought that it might be associated with some other particle associated with the nuclear forces. It wasn't. That, as far as we know, is just a coincidence. And the muon is some heavier cousin of the electron that we know exists because we've measured it, but doesn't really pop out as a prediction of any unified theory that we know of yet. This obviously doesn't stop theorists from trying. So on the other side, some particles really were predicted by theorists that need to show up for our basic understanding of quantum field theory to be right. And one of these goes by the name of the charm quark. You can tell how physicists felt about particles at the time whose names vary from strange to charm. And so in the 1960s, theorists were working on the idea that protons and neutrons aren't elementary particles. They're made of smaller elementary particles called quarks. And at the time, there was indirect evidence for 3 types of quarks that would make up protons, neutrons, other particles that people had detected. But in 1970, a few theorists, Glashow, Iliopoulos, and Mayani, predicted that you actually need a 4th quark to reconcile different observations about the weak nuclear forces. That if you look in detail at all our measurements of the weak force, they don't actually give a consistent set of predictions unless you add this new particle to the model. And they were able to predict roughly what its mass should be in order for all of this to make sense. Lo and behold, experiments at Brookhaven Lab and the Stanford Linear Accelerator Complex in 1974 both discovered direct evidence for the existence of this fourth charming quark in the form of these peaks in the event rate for scattering processes. And this is the initial data from the 70s. And the same peak here around 3 GeV, you can now see in exquisite detail in data from the first couple of runs of the LHC. So charm quarks have now been extensively studied, and two other yet heavier quarks, the bottom and the top, were then discovered here at Fermilab. The bottom quark in 1977, and the top quark took a while to actually pin down, but was eventually discovered here at the Tevatron in 1995. What's on your mind?
What was the method used to discover said fourth, fifth, and sixth quark?
Good. So it's a classic method in particle physics of take two particles that you can accelerate really fast, smash them together, and measure what comes out. So these were really early collider experiments. Initially, electron-positron colliders are a really good source for producing charm, anti-charm, and other particles. Here at Fermilab, we had a proton-anti-proton collider that was the one that discovered the top quark. But as you'll hear more about in the next talk here, physicists have been creatively smashing particles together to see everything that can be produced when you shove lots of energy in one place to great effect over the last almost 100 years. So this brings me to the other quarks and my favorite particle, the underrated gluon. And these particles were known long before they were understood. So the same cosmic ray type experiments that saw the muon and the positron also started seeing this zoo of other particles called hadrons. And in order to give some organizing principle to this zoo of particles, theorists noticed that there were symmetries among them that would make sense if they were all composed of three different particles with different properties of charge and mass. And the hadrons that the experimentalists had previously just dubbed strange because they did weird things in detectors could all be somewhat unified under the description that there was one strange quark, as well as an up quark and a down quark, which are the ones that make up protons and neutrons. And these diagrams sort of show how you can classify the different hadrons that were seen at the time in terms of the content of these quarks. However, this idea was initially met with some skepticism. It could explain these sort of patterns in the data, but no one had ever seen a quark or any evidence that protons were really made of other smaller elementary particles. You can't smash them and get quarks out. So the experimental validation of the quark model in earnest really happened in the 1970s, where experiments at SLAC and elsewhere discovered that the scattering cross-sections for reactions involving protons that are crazy complicated at energies of a few GeV, where you have those peaks associated with the charm quark, are simple when you go to high energies and follow some simple scaling laws that are what you'd expect if they were made of elementary particles. And theorists got better at making predictions directly from this quark model. They were able to include the gluons, figure out that the results should be not exactly the same as you'd get if you had the proton made of just free quarks. And those predictions gave beautiful agreement with the accelerator data coming out of SLAC and other colliders. And the surprising feature that emerged out of this is that, unlike electromagnetism, the forces between quarks in this theory of quantum chromodynamics, or QCD, become stronger at large distances. So instead of the force sort of falling as you separate charges in electromagnetism, it's like quarks and antiquarks are bound together by some string whose force stays constant as you're pulling them apart. And so you'd need infinite energy to totally separate the quarks inside a proton, which is why we never see them separate. But on the other hand, if you get to really high energies, then the descriptions of quarks and gluons simplify because their interactions become weak. And this is in large part why we've had so much success as a community in pushing the energy frontier forward, since through the heroic effort of our experimental colleagues to build better colliders, theorists have an easier job of being able to make predictions from QCD that are accurate in these high energy environments. And predictions went on to not just validate the existence of quarks, but actually get some more or less direct evidence for the existence of gluons from the fact that when you have some event that emits a quark and an antiquark, you get these jets of energy that are sort of collimated beams you measure in your detector. And that tells you that you had two particles flying away back to back. That would be the quark and the antiquark that were expected here. And then experiments like at DAISY in 1980 showed these beautiful 3-jet events where there are 3 collimated beams of energy that hit your detector. And if all you have are quarks that have to be produced in quark-antiquark pairs, you can never get this kind of 3-jet event, making it more or less relatively direct evidence that there's also these gluons that really exist as particles inside of protons and neutrons. At low energies, I think it's fair to say QCD is a mess. Protons look like tangles of many quarks, antiquarks, gluons of indeterminate number fluctuating around in the vacuum. By weight, you are approximately 2/3 the energy of gluons, maybe 1/3 the energy of quarks moving around, and only about 1% of your mass actually comes from the elementary mass of the quarks that's involved. You are all bundles of radiant gluon energy. Predicting those, of course, is hard for theorists. And so for low energy QCD, we need to turn to numerical simulations that go by the name of lattice QCD, which is, as Gray alluded to, what I mostly work on here at Fermilab. And these sort of simulations have been used to predict the spectrum of hadron masses directly from the underlying theory of QCD. Here's a nice summary plot from 2012 from Andreas Kronfeld here at Fermilab, showing the simulation results at the time in these colored points and how they line up with the experimental predictions for the masses of different hadrons in the black lines here. And so a question that I'm really interested in is how far we can push this and try and start directly from our theory of quarks and gluons and predict not just the mass of the proton, but the beginnings of nuclear physics and the reaction rates for protons fusing into other particles inside of fusion accelerators. And there's lots of interesting directions here in terms of scaling up our understanding of the standard model in order to really grapple with the complexity of low energy matter and nuclear stuff. And this is a nice intersection of pen and paper theory, formal math, but also high performance computing on some of the largest supercomputers in the world to be able to get accurate enough simulation data. And so research in this direction has really grown along with the growth of computing hardware, the development of things like GPUs. And it's interesting to look at this moment as how new technologies in computing, like AI, maybe somewhere in the future, quantum computing, could really make a difference in how we approach these kind of computational physics problems. And I think it's a really interesting frontier that's opening up here. Okay, and that's about it for the quarks and gluons. The other force that I want to give its due here is the weak nuclear force, because it gives an example of how sometimes theorists think that we know everything, and we're wrong. So in the 1950s, if you polled theoretical physicists and asked, does the world look the same in a mirror? I'd expect you'd get a lot of yeses. And a couple of theorists, Li and Yang, in the mid-1950s, decided to actually see how robust the data for this is. Do we really know experimentally that the laws of physics look the same if we reflect the world in a mirror? And data for electromagnetism and for the strong nuclear force give a pretty unambiguous yes, that if you reflect your experimental setup like in a mirror, the results come out the same. For the weak nuclear force, there wasn't really clear data on this, and it was kind of ambiguous. And so Li and Yang made a bold proposal that someone should really go out and test whether the weak force looks the same in a mirror. And the Wu experiment done, you'll note, in the same year as this proposal, in a heroic effort, gave an immediate no, absolutely not. The decay rates of certain radioactive beta decays are completely different depending on the orientation of the nucleus. And in some sense, it's the left-handed electrons that are always emitted in these beta decays. So this provided a challenge and opportunity for the high energy physics community to understand what's really going on here. What are these new rules that look different in a mirror? And theorists' best ideas for explaining these postulated the existence of two new particles called the W and Z bosons for, I believe, the weak force and zero charge, since the Z was a neutral particle. And the Z predicted then that you would have these neutral currents associated with the weak force, which hadn't previously been seen, but were then detected in the 1970s. And so by the 1980s, we had pretty good predictions for what the masses of the W and the Z should be. And accelerator experiments at CERN were able to go test these predictions of the standard model. And this was really a moment where the world was on the edge of its seat in understanding whether we understood how the laws of physics work. The Queen of England actually requested that CERN secretly wire her the results of the experiment before it was released to the public in case there was going to be a moral panic or something, I don't know. But CERN validated the standard model. The masses of the W and Z came out as predicted. And this gave a lot of confidence that we really had the theory of the weak interactions under control. Except there was one additional particle that you absolutely need. Yeah, go ahead.
How do you put like really small particles in here?
How do you put really good? You don't actually use a mirror. You just test how things that would flip if you looked at them in a mirror. So like if you think of a spin of a particle, if it's spinning counterclockwise, if you look at my hand in a mirror, it looks clockwise instead of counterclockwise. So that's the key sort of thing is you measure the difference in an event rate between the clockwise spinning electrons and the counterclockwise spinning electrons. Does that make sense? Sweet.
So it's all mostly theoretical. If you can't actually measure it like in a mirror, it's just theoretical on what calculations would be.
Yeah, I mean, you have a theory of what a mirror means, but that part physicists mostly agree on, that you can't really, even at just sort of the level of a classical top, come up with a consistent theory where something that's spinning counterclockwise when you look in a mirror is still spinning counterclockwise. A mirror really has to flip spin in order to get a consistent definition of a mirror reflection. But this is something that theorists really think about, and realizing when people have made some assumption that they haven't thought deeply about in these kind of questions is, the key job of scientists, is to really always question those assumptions. Cool. Okay, so the last missing piece of the standard model puzzle then for explaining the weak interactions and everything else is this particle that you may have heard of called the Higgs boson. And the Higgs has a very special role in the standard model. this nice block chart from Chris Quigg sort of organizes all of the particles in the standard model. And it points out that the quarks actually come in 3 different colors. And gluon interactions you can think of as kind of exchanging the colors of the quarks. The weak interactions you can think of as turning an electron into neutrinos or turning one type of quark into another. But all of these interactions only link left-handed things with other left-handed things. But if you want a particle mass, you need to somehow be able to turn a left-handed thing into a right-handed thing. And this requires the existence of some new interaction, some new particle. And in the mid-1960s, a collection of theorists, including, of course, Higgs, realized that there was a mechanism that you could link this up, but that you would get this distinctive kind of particle that doesn't have any spin. It would be the only one of those we've ever seen as an elementary particle, and it would have to have some relatively heavy mass in order to pull this off. And so since the 60s, everyone has been looking for the Higgs boson or one of a dozen other theories that theorists have since come up with for how you could pull off this connection that would let particles get mass, even though the clockwise and counterclockwise particles are different. Long story short, in 2012, the ATLAS and CMS experiments at the LHC both reported a statistically significant discovery level detection of what they called at the time a Higgs-like boson, because you want to be careful. They hadn't observed all of the properties you need to say this is the Higgs boson, but they saw this bump in the event rate for proton-proton collisions at this particular energy in the right sort of way for a Higgs boson to be responsible for those extra events. And you'll hear much more about the beautiful physics the LHC has done since in the next subsequent talks after me. But safe to say that so far we've gotten a beautiful picture of an unprecedented wealth of data that so far is consistent with this not just being a Higgs-like boson, but the Higgs boson of the standard model. And so far, theory is holding up to the experimental test at the energy frontier. The last frontier that I want to mention then are the neutrinos that we haven't talked about too much so far. And this is another good example of, oh, is there a question in the chat? Okay, we'll circle back if there is. Okay, so neutrinos are flying through you as we speak. There's millions of neutrinos that are passing through you coming from the sun. They're just very hard to actually detect. But they're released whenever you have nuclear reactions, including proton-proton fusing into a proton-neutron nucleus called a deuteron, emitting a positron and a neutrino. And this sort of interaction, followed by subsequent things in this chain getting fusion from hydrogen up to helium, are some of the reactions that really power the sun. And so if you know how much light the sun is emitting, you know how many neutrinos per photon should be emitted from this description of the reactions, then you'll get a nice prediction for how many neutrinos per second the sun should be emitting. And back in the first half of the 20th century, this was thought of as a really nice way to test our model of nuclear astrophysics, test our understanding that the sun is a big nuclear reactor powered by fusion. And heroic experiments at the Homestake Mine in South Dakota in the 1960s detected for the first time the neutrinos emitted from the sun. These were putting tons of something like chlorine cleaning fluid underground in a mine and sifting out individual argon atoms that had been hit by a neutrino and transmuted from chlorine to argon. And they found some. However, they found less than half the number that was predicted by nuclear theory. And at first, the community went, OK, Ray, this was a super hard experiment. You're counting individual atoms, could have underestimated your systematics. Let's give it time. But over the next few decades, neutrino experiments continued to show this deficit, that there were about a third as many neutrinos as we expect emitted from the sun. And what was eventually realized is that theory of nuclear astrophysics and neutrino detectors were both right. There was this amount of neutrinos emitted from the sun that we expected, but the neutrinos oscillated into different flavors mid-flight. You started out with a beam of neutrinos associated with the electron. You end up with a mixture of things associated with the electron, but also things associated with the muon, and a third neutrino associated with one yet heavier cousin of the two. And this roughly equal splits between the three neutrinos is what ends up giving you this third as many as you expect by the time that you measure them. The reason that we believe that that initially kind of crazy sounding story is true is that there have now been experiments of solar neutrinos, of neutrinos produced in atmospheric collisions, of neutrinos produced in reactors and accelerators, and we've built detectors that are able to detect not only the electron type of neutrino, but the other two types of neutrinos as well. And so the Nobel Prize went to Snow and Super K for being able to detect all of the types of neutrinos for the first time and validate that we indeed do see the right total number of neutrinos. They've just gotten mixed up between the flavors in a way that theorists didn't see coming until it was measured. And so there's future experiments under construction, including here at Fermilab, where we're planning to produce the world's most intense beam of neutrinos. Shoot it 1,300 kilometers underground through rock to the bottom of a mine in South Dakota, very close to the mine where solar neutrinos were initially detected, and then detect the neutrinos there. And then we're going to repeat this with our magnets flipped the other way so that we produce antineutrinos, so that we can look for differences between how the neutrinos and the antineutrinos do this oscillation business. And these kinds of subtle properties of neutrinos are very hard to measure, are very delicate, but could have really important consequences for even the physics of the early universe, where we know today that we have a world that's made up of matter with very little antimatter. Right after the Big Bang, we'd expect a fireball of roughly equal amounts of matter and antimatter. And so there's some big unsolved theory puzzle as how we end up with matter at the end. Why didn't it all just annihilate with antimatter? And perhaps the leading theory for that, how that might have actually worked, hinges on neutrinos being able to flip into antineutrinos and some asymmetry between the way they oscillate being the seeds for why the universe ends up having matter and stuff in it at all. So there's really beautiful connections between these kind of accelerator neutrino experiments, other sorts of neutrino experiments, early universe cosmology, and high energy fundamental physics.
Why are there three different types of neutrinos? So when they come out of the sun, they're like the electron ones.
Yep.
Then they turn into the three different types.
Yeah. That is a great question. That is something that keeps theorists up at night. So I want to come back to this sort of schematic picture from Chris Quigg, who has a really nice recent post on the archive where physicists like to post upcoming research asking exactly these sort of questions. What are the puzzles that we just don't understand? And why are there three different copies of all of these particles is absolutely on the list. The only cute fact I can give you is that this neutrinos and antineutrinos oscillating differently requires at least 3 generations of particles. So maybe that's important. Maybe 3 generations is what we need to enable a matter-dominated universe. But now we've walked into the realm of theorists speculating by the coffee machine, not things that we really have data for.
You say at least 3.
Yeah.
Are theorists unsure if there's maybe 4 or 5?
Great question. So collider experiments have enough data to show that it is impossible to have a 4th generation that's exactly the same as the other 3, but heavier added on. You can do lots of other things to add other particles to this, but it's now ruled out by data to add just an additional 4th generation, nothing else. So other questions in this vein. As I said, we don't know whether neutrinos can turn into antineutrinos. We also don't really know how many neutrinos there are. We know there's at least 3 because those are the ones that we interact with, but every other particle has a right-handed counterpart. We only interact with the left-handed neutrinos because they only interact via the weak force. So are there right-handed neutrinos out there that we just don't have any way to interact with except gravity? We don't know. Could they be dark matter? We don't know.
I was wondering, why are neutrinos like only associated with leptons?
Yeah, that's a great question. Within the standard model, the pairing of an up-type quark, a down-type quark, an electron, and a neutrino has the right combination of charges to give a theoretically consistent model. If you start adding other particles with standard model charges, then most charge assignments that you'll pick will end up being inconsistent. So this is one pattern that works. It's not the only pattern that works. Why this pattern, we don't know. Other things we don't know. What other particles are missing? What is dark matter? There's also dark energy. We don't even know if a particle description of that is right in the first place. We don't know, as I alluded to earlier, how to really think about the complexity of nuclear physics and chemistry emerging from the standard model. We should be able to describe all of the low energy properties of table starting from the standard model Lagrangian. We can't do that yet, not because we don't have some understanding of what the rules should be, just because we're not skilled enough yet at describing super complicated systems directly from these rules. And yeah, finally, as we've already sort of called this one out, there's lots of other choices for these masses, lots of other choices for these couplings. Why this one? And then there's the elephant in the room of gravity that I mentioned in the beginning and haven't come back to since. Gravity can be added to the standard model, and at low energies, everything seems hunky-dory and fits together. But the high energy behavior of gravity becomes mathematically inconsistent and shows that quantum field theory, as we know it, at least in the approximations we're able to compute it, doesn't give a complete theory of gravity. So we know from that really there's something fundamentally incomplete about our description of reality. And I think that makes it a really fun time to explore physics. So that's where I want to leave you all. And I'll be happy to take any more questions on both the things we know about the standard model and the things we don't know and are having fun thinking about. Yeah.
Since gravity is the weakest of the 4 forces, if right-handed neutrinos can only interact that way, are they detectable at all?
They become really hard to detect. So astrophysics gives most of our data about dark matter, which is something that, as far as we know, only interacts gravitationally. We know really that it exists because if you look at like ways that you can estimate the mass of a galaxy from like how fast it's spinning as a function of how far out you go, that there's much more mass there than number of stars you can count times mass of star. And we have other more direct observations of sort of gravitational pulls on things by invisible objects. So there's dark matter out there, but actually detecting this in a lab is really hard. People are thinking about it. There's really cool experimental proposals. You can Google one called Wind Chime that's trying to build like some array of like molecular chains that you'd sort of build up some coherent interaction across. I can't understand it nearly well enough to explain it, but suffice to say, people are thinking about it. It's really hard.
Is there a difference between antimatter and dark matter? Or
Yes. Yeah. Antimatter is, in some sense, very nice, well understood. We've known it exists for 100 years and can write down all of its properties. So all of these particles here have an antimatter counterpart that you can describe just by flipping the signs of all of the charges. And we can produce antimatter in a lab in small quantities. We can measure its properties. Everything seems to hang together. Dark matter is what we call stuff out in space that is interacting with gravity. So it's like matter, but it doesn't glow. It doesn't emit any light. And so physicists, again, with really creative naming, stuff in space that has mass that we can't see, dark matter. And we have no idea what it is.
In like a collision where you produce neutrinos, do you know like what kind of flavor neutrinos produce first, or is it kind of just indiscriminate?
Yeah, it's the same flavor as your incoming particle. So that's why in the sun, it's always up and down quarks and a proton make an electron. You always get an electron type neutrino as the other particle that's coming out. Like in the accelerator experiments that we're building here at Fermilab, you end up producing a beam of muons and hitting it with a target, then that gives you a pretty good beam of muon type neutrinos. Cool. Anything else? Oh, yeah. All right.
And Nate, are there any questions on the Zoom?
I think right now we might see them because they're only privy to the host or people that have been upgraded.
Good. Then let's see if I can see them.
Should be able to see some.
Yeah.
Yes.
Okay. Does the behavior of the W and Z particle account for the changes in the electron particle decay of a mirrored world? Yes. The key property is that the W and the Z only interact with left-handed particles. So they're a force that only interacts with, if you want, counterclockwise spinning things and doesn't interact at all with clockwise spinning things. And that is where the asymmetry comes from. Another one is asking what exactly, oh, I'll come back in one moment. What exactly is an event rate? So that's just most collider type experiments in particle physics start by colliding some beams that will produce particles, and then you detect particles via some deposition of energy or something in your detector. And so the event rate is just the number of particles you think you've seen of a particular type in an experiment.
Do we know why why there's asymmetry in the first place?
No, why the weak interactions only interact with left-handed particles, whereas everything else interacts equally with left and right? Big mystery. And do we have anything else in here? No, that looks like it in the chat. Okay, yep.
If dark matter doesn't emit light and we don't exactly know what it is, how do we know it exists?
Good. We know it exists from astrophysical observations, that there's ways in which you can infer the mass of a galaxy. And we also know roughly how much mass stars have based on how much light they emit. And the simple way to think about it is that there's observations that tell us how much total mass a galaxy has, and it's way more than the amount of mass that could be explained by the stars that are shining. So we know that all galaxies are kind of like disks of light, but then there's like a spherical halo of mass around them that seems to be what actually influences gravity, and it doesn't emit any light. So that's our dark matter picture. But it's very galactic, astrophysical. We don't really have handles on it in the sort of experiments that we do here at Fermilab, although we're trying. There are lots of experiments searching for various different models of what dark matter could be, but all of our positive evidence is really based on measurements of gravitational properties of things in space.
what's the difference between like a particle oscillating versus spinning? Because I know like neutrinos oscillate, but then all particles like have a spin.
Yeah, that's a great question. Thank you. So the question was, what's the difference between neutrinos oscillating and particles spinning? And spin, it's weird that particles have this property called spin. I can't really give you a why spin should exist, but it's a fact that all particles carry some angular momentum. They act kind of like a spinning top that can either have a clockwise state or a counterclockwise state for most of the particles. And so a particle that's spinning counterclockwise will continue propagating, spinning counterclockwise happily unless it runs into some other particle. The neutrino flavors we think of as different particles because they have different masses. Like the left and right-handed spinning electrons will have the same mass. The different neutrinos have different masses. And so we use oscillations to refer to flips between particles of different masses as opposed to just a particle carrying some angular momentum that it can give and make other things spin. Does that make sense?
Yeah.
Do you think it's possible to collide two quarks together or work with a particle?
No, it really seems to be pretty robust that it truly would take an infinite amount of energy to liberate a quark from a proton. So you really can't get a good quark beam source. The closest we can get is there are experiments at RIC at Brookhaven and also at the LHC that have smashed initially big nuclei like gold, also now smaller things, but the easiest things to picture are big heavy ions that you smash together hard enough that the middle becomes this fireball where the quarks and gluons melt. And you end up having, there's this phase of matter called a quark-gluon plasma, where you no longer have a good description in terms of protons and neutrons, but your medium really looks like quarks zipping around interacting with gluons. And so the best situation for trying to do that would be produce some sort of quark-gluon plasma and then try and hit quarks in it with beams. This is obviously really hard, but people have looked at tagging like quarks coming out of this sort of plasma and being able to measure their properties has taught us a lot about how quarks and gluons interact when they get really hot.
So when you said that we weigh a lot heavier than what our actual mass is if you took all of our atoms combined, where do we get that extra mass from?
So from energy. So this is really E equals mc squared in its full glory, that the average energy stored by light particles moving around really quickly acts just like mass. And so it's the energy of these light quarks and gluons zipping around really fast, carrying lots of momentum, interacting with each other. That energy ends up being what forms most of the mass of a proton when it's sitting around.
You see the energy is just like mass, but like what differentiates it from mass? Like,
yeah, that's a great question. Mass is how much energy something has when it's at rest. I think that's the cleanest definition. And energy really is the more sort of general concept, unless you're talking about like some specific particle, how much does it weigh at rest? That's a nice, well-defined question that mass is the answer to. Yeah, all these things get confusing.
One on. This, well, I thought heat was simply the motion of atoms or particles. Does this affect subatomic particles like quarks?
Totally, that's a great question.
Quark gluon plasma have temperature, I guess.
Yes, exactly. The quark gluon plasma does have a temperature, and it's when you heat quarks and gluons up to some, oh, I wish I knew it in astronomical units. It's an unbelievably high temperature, like hundreds of mega electron volts. But what that actually is in Kelvin is escaping me. But if you heat things up to this supremely high temperature, then they melt at the subatomic level. On the other hand, for a proton sitting at rest, there is some contribution to its energy from that sort of heat, from just like the vibration of the particles inside. That is a much smaller contribution than this other like rest energy of the quarks and gluons. So a proton sitting around will have some temperature associated with it, but it's really, really cold.
If we're made of energy, how come we don't like lose our energy? I don't know.
Yeah, that's a great question. And a lot of the answer is statistics, which is kind of strange and unsettling. But when you have huge numbers of particles, things behave like their average values with very small fluctuations. And so the energy is fluctuating inside of a proton, but the fluctuations are on such rapid subatomic timescales that in any sort of human process, you're really only seeing the average of many snapshots of these subatomic interactions, and that makes things look as though they have these really definite same every time kind of values.
Well, I think we should probably pause, take a break here. Thanks for all the good questions. Let's thank our first speaker, Mike. A great talk. We have another great speaker coming. 5, so that's like 6 minutes, because we got to keep the schedule today. But if you need to use the restroom, get some water, we'll be back in about 6 minutes.
Thanks everyone for all the great questions.
Hey, folks in CMS control room, I just want to add Christina Wang as a panelist, our next speaker. Yes, in a moment.
I said nice. So I'll let Nate introduce, but first two announcements. So first, there's one person who's here who didn't check in with Allie at the beginning. So if you didn't check in with Allie, please do that. We only have 31 people counted here, but there's 32 of you. So if you want to be counted for attendance, just make sure that you're checked in. And you can do that at the end of the lecture while we're turning around for CMS for the virtual tour. One other announcement. So questions in the room, people can hear them online, but it's helpful if you speak up. So please speak up while you're asking the question. And if you're a little quieter, we'll also have the speaker asked to repeat the question for the people on Zoom. Okay.
All right. So yeah, we're back to the second half. So first half, we learned about the standard model. Now we're going to learn about one of the experiments or some of the experiments that test the standard model and really, put a microscope to this beautiful standard model that has been, built up over the years. So we have Christina Wang, Dr. Christina Wang to speak to us. Christina went to college, got her undergraduate degree from MIT, and then went on to get her PhD from Caltech, where you worked on CMS, I believe, largely. I think there's some dark matter related studies during your SGCSR, dark matter analyses. But yeah, Christina has a lot of knowledge about the CMS experiment and physics at the Large Hadron Collider, and she's here to share that with you. So let's give her our attention.
All right, thanks for the introduction. I think you can hear me well. So yeah, I'll be talking to you about physics at the Large Hadron Collider. So you've already heard a lot about the standard model. So at the Large Hadron Collider, the main purpose is to first to be able to understand the standard model prediction precisely, and also to search for any hints of physics beyond the standard model. So I guess first of all, why do we need to build a high energy particle collider to be able to understand the standard model? And I guess the short answer is we want to study particles on a very small scale, on small distances. So just to give you I guess I can use this. Just to give you kind of a scale of things, the atoms from this diagram, the atoms have a scale of on the order of 10 to the minus 8 centimeter. And the nucleus that are inside the atom make up of less than, I guess, 1/10,000 of the space in the atom. So the nucleus has a size that's about 10,000 times smaller. They're about 10 to the minus 12 centimeter. And then within the nucleus, they're made up of things like protons and neutrons. And they're on the order of about even 10 times smaller than that. And the protons and neutrons you've heard in the previous talk are made up of things that are called quarks. And these are on the order of 10 to the minus 16 centimeter. And these are the elementary particles that we're interested in studying. And you've also heard from last week that we can describe particles as waves. So for a particle with an energy of E, we can describe its wavelength from this formula up here, where the wavelength equals to hc divided by, no, I think it's fine. Hc divided by its energy. So essentially the energy is inversely proportional to the scale that we're able to probe. So to be able to study things on the very, very small scale, we need to boost the particle energy to extremely high energy. So here on this diagram, you can see that basically for our bare eyes, we can probably see things on the order of, at smallest, on the order of a few millimeter. And if you use a microscope, you can probably see things on the scale like bacteria on the order of 10 to the -8 meter. That's around here on the scale, while the LHC is way, way down the line where we're interested in things on the order of 10 to the -18 meter. So now you kind of have a feeling of what scale we're looking at, but what level of energy we're talking about here. So the units that we usually use in high energy physics is not in joules, but in this unit called electron volt, which is essentially the energy for an electron, or it's essentially the energy that electron can gain over 1 volt. And we usually use this unit called 1 giga electron volt, which is about 10 to the 9 electron volt. And that's roughly the weight of a proton, which translates to about 10 to the -24 grams. And at the LHC, we're colliding protons at the energy of about 13 TeV, which is high enough to be able to probe length scales on the order of 10 to the 19 meter, which is smaller than the scale of quarks. Also, if you have any questions, feel free to interrupt during the talk. You don't have to wait till the end of the talk. So let's do a quick short exercise. So how many AA batteries do you think are needed to be able to accelerate an electron to 1 giga electron volt? So there are 3 hints here. So one is the conversion between electron volt to joules. And the second one will be able to give you the energy of the AA battery. And the third one is the equation to calculate energy from the power and time. So I'll give you a couple of minutes so you can discuss with the folks around you. And if you have any questions, feel free to speak up. In B, the units in B?
Yeah.
It's milliamp hour. So a quick hint, if you want to calculate the energy of the battery, you basically just multiply these 2 numbers. The milliamp hour multiplied by volt to get the energy of the battery. I see some of you are calculating. Or if you have any ideas of how to proceed, you can also. Calculate. Does anyone want to give it a shot? Okay, I'll go straight to the answer. Yeah, so basically from this hint B, you're able to calculate the battery or the energy of a single AA battery, which is essentially the multiplication of these 2 numbers. I guess one tricky thing is you have to convert the hour into 2 seconds to actually get to joules. So in the end, we get about 12,000 joules per battery. And then you'll use the first hint here to convert the number of joules into units in EV, which is essentially a humongous number. At the end, we get about 8 times 10 to the 10 TeV. So 1 battery is more than sufficient to be able to accelerate an electron to 1 GeV. But now you may wonder, this seems like a huge number. It is basically, 1 battery has much more energy than the LHC. Are we missing something here? So one thing to note is that at the LHC, we're accelerating single protons, while in this case, we're looking at the macroscopic energy in a single battery where there are trillions and trillions of electrons and protons within a battery. And another thing is it's also extremely hard to accelerate the particles when it gets too close to the speed of light. as you've also heard about in the previous talk, because when the particles are accelerated close to the speed of light, of course, their kinetic energy increases, but also their effective mass or their energy increases as it gets to close to the speed of light. So essentially, it gets harder to continue accelerate them as it gets heavier. So here you can see the equation of their effective mass, where E equals to mc squared, where m is its rest mass, so the mass of any particle when it's at rest. But as you can see, the velocity starts to start to have a role here, where as the velocity gets close to the speed of light, the energy or the effective mass starts to increase. Yeah. C is speed of light in vacuum, so it's a constant here. So as you can see, when the velocity is very, very small, like at the classical speed, that's small compared to the speed of light, then E equals to mc squared. But as you get closer to the speed of light, then the effective energy starts to increase. Yeah.
Where does that equation like come from?
That's a good question. So I guess it's derived from relativity. So yeah.
Which we will hear about from next week. So actually, next week I think we'll
Oh, okay.
we'll go through this a bit more directly.
Okay, good to know. Yeah. Yeah.
If you could reach the speed of light, if V equaled C, would you be dividing by 0?
Yeah, that's a good question. So it is actually very or almost impossible for particles that have a non-zero mass to actually reach the speed of light. So for example, at the LHC, the protons are at the speed of like 99.999% of the speed of light, but it never actually gets to exactly the speed of light. Yeah. Yeah.
Light not
Yeah, so photons have a mass of 0. Yeah. No, yeah, that's a good question. Yeah.
Why can we never achieve speed of light?
I guess realistically, it will take a humongous amount of energy to be able to. So as I mentioned, the effective mass increases as you keep increasing the velocity. And you have to put in more energy to increase. So for example, if you have a particle that has that's at rest, it's very easy to increase the velocity to, let's say, 10% of the speed of light. And it's also easy to go from 10% to 20% of the speed of light. But as you're at like 99.999% of the speed of light, it takes a huge amount of energy to keep increasing the velocity by even like 0.001%. Okay. So yeah, so that was kind of the gist of this slide. So essentially, to be able to accelerate protons to about 13 TeV or very close to the speed of light, we need very powerful electromagnetic fields and special magnets to be able to accelerate these particles in a small space. So to be able to do that, we built the Large Hadron Collider, which is a 27-kilometer ring that's located about 100 meters underground. That's hosted by CERN, which stands for European Center for Nuclear Research in French, so it doesn't exactly spell out to CERN, but it's an international physics laboratory that's close to Geneva. So here you can see roughly where it is on the map. So it's actually partially in Switzerland. So this part of it is in Switzerland, while this part of it is in France. So CMS is actually in France, while Atlas is in Switzerland. So what's inside of the LHC? So essentially LHC is made up of 2 separate rings. So within one ring, the particles or the protons circulate clockwise, while in the other ring, the protons circulate counterclockwise. And the protons are not distributed continuously within the ring, so they're grouped into little bunches, as you can see from this little diagram. So they're grouped into little bunches, and each of these bunch are 7.5 meters apart. So overall, at a given amount of time, there are usually about 3,000 bunches around the ring. And within each bunch, there are about 100 billion protons, which may sound like a huge number, but actually it's only 5 nanogram of protons. So a fun fact is that the amount of protons that we're using in the LHC is so small that one hydrogen bottle is enough for about 200,000 years of continuous operation at the LHC. So each of these bunches basically circulate the LHC for about roughly 20 minutes to reach the total energy of about 6.5 TeV. And then 2 of the bunches, so here you can see at the collision points, essentially the rings will cross each other. So the bunches will be able to collide at about 13 TeV in total. And when the bunches cross each other or collide with each other, it's actually the partons or the quarks and the gluons within each protons that are interacting. And the partons only usually carry a fraction of the total proton energy. So there are 4 main experiments at the LHC, or in other words, 4 points where the protons can collide. One of them is called ELISE, where we study collisions of actually heavy ions, so not protons. And another one is also a more specialized experiment called LHCb, where we study particles that contain heavy quarks. So for example, like the B quark. The 2 that I'll mostly be focusing on today is actually the 2 general purpose detectors that we have at the LHC that are located diagonally from each other. So I'll go into what I mean by general purpose. So when we say general purpose, we mean we want to aim to study almost everything that comes out of the proton collision. We want to be able to measure precisely what we already know, what already can be predicted by the standard model. So by measuring things like mass of the particles, how often different particles interact with each other, we'll be able to see if there are any deviations from the theoretical prediction from the standard model. And we also we try to cast a broad net to look for new things that we've never seen before. So for example, we look for dark matter or even things that we haven't even thought of yet. So to be able to do that, we need to build a detector around the collision point to detect as many particles as possible. So we want to be able to see what are the particles that are produced after the collisions, the number of particles, the identity of the particles, the velocity, topology of these particles, to be able to also measure the energy and momentum precisely. So our detector is mostly, I'll go into more details of how our detectors actually look like, but a very, very simplified diagram is essentially we design detectors kind of like onions to cover the collision point with a hermetic geometry, and they're shaped like an onion. So we have different layers of detector around the collision point. So the particles that we're able to detect depend a lot on the lifetime of these particles. So I'll split them into 3 categories. So if the particle has an extremely short lifetime, that they decay immediately to other particles even before they're able to reach, for example, the first layer of our detector, then we're never going to be able to detect them directly. But of course, it's not to say that we don't know anything about it, because we can detect the decay particles that it goes into. And then by measuring, for example, the energy of these decay particles, the angle between these the decay particles, we can infer about the properties of the parent particle. And in addition, we also have medium lifetime particles. So for example, it may reach some of these detector layers, and then it will decay to additional particles. So for these particles, we can actually use these displaced signatures to be able to identify them. And the particles that we're actually the best at detecting are these stable particles where they traverse through all of our detector layers. And so we can measure their energy and momentum precisely. So just to give you some examples of what are these different particles with different lifetimes. So here you can see kind of a diagram where the y-axis is the particle mass and the x-axis is the particle lifetime. And these different dots correspond to different standard model particles that we know of. So some of these short lifetime particles, including, for example, the top quark, Higgs boson, Z boson, and hadrons. While if the particle has a medium lifetime, which corresponds to about a few millimeter to 10 meter, which is similar to the size of the CMS detector, then they would decay somewhere in the middle of our detector. So some of these particles include tau lepton and additional hadrons. And the particles that we're actually more familiar with and are better at detecting are particles that are stable. So they would traverse through our entire detector, so including muons, electrons, photons, and additional and neutrons and pions or protons. So, so as I mentioned, our detector is actually mostly optimized to detect stable particles. So these hadrons, photons, electrons, and muons. And if these particles come from the decay of the short lifetime particles, we can also infer the existence of these short lifetime particles by, for example, analyzing the relationship of these decayed stable particles. So how do we actually measure these particles with our detector? I'll go through a short exercise where we can design a very simplified LHC experiment. So first of all, we need to determine what geometry we would like the detector to be. So essentially designing a particle detector is like playing Pokemon. We want to try to catch everything that comes out of a collision. Or the other analogy that I really like is like building a camera. You want to film basically the collision event. You want to make sure your field of view is as large as possible. You are able to see the entire collision point. And you want to make sure your frame rate, for example, of the camera is fast enough to be able to catch all the particles that come out of the collision point. So first of all, we want to make sure, so if you look at this diagram, we'll basically have two bunches of proton, one coming in from the left, one coming in from the right, and they will collide at this point here. And most of the particles will actually fly out vertically up and down because the net momentum of the two protons are going to be 0 if they come in at the same energy. So essentially, if you look at it from the cross-sectional view, we'll have most of our activities flying out in the transverse plane. So which is why we designed our detector to be a cylindrical shape. So to cover all of the angle in this direction. And then we leave some space, of course, for the protons to come in. So after we decided that we want to build our detector in a cylindrical shape, we want to basically need to add a magnet in the detector to be able to bend the charged particles. And this will allow us to measure the charge and the momentum of these charged particles. So essentially for any charged particles, they will be impacted by the force of electromagnetic field. And if the particles have a very low momentum, they will be very easily impacted by the B field. While if it has a high momentum, it's harder to impact their trajectory with a given B field. So by basically measuring the radius of the curvature, we're able to measure the momentum very precisely. And by checking the direction of the curvature, so whether it curves to upward or left or downward in the slide, then it tells us whether it's, for example, a positively charged particle or a negatively charged particle. So then we want to make sure we need this magnet to fit into the cylindrical design of our detector. Does anyone know what's a magnet that would fit, that would give you a uniform B field that would be in the cylindrical shape? Any idea? So the answer is a solenoid, which is essentially coils of current that are routed in a cylindrical shape that will provide a uniform B field essentially in the Z direction. So, so now we have the magnet, which will bend the trajectory of the particles. Then we need to build something that can actually measure the trajectory of the particles precisely. And so we do this with the silicon tracker. So essentially they look just like our camera, where they have essentially tiny pixels in the detector layer. And then we build multiple layers across the trajectory of the particles to be able to intercept the trajectories, so that by connecting the dots in the different layers, we can map out the trajectory of the particles very precisely. And one requirement of the tracker is that they must be, or I guess two requirement is that first, we need to be able to register the hits from the charged particles. So we need the particles to deposit some amount of energy in each of these layers to register a signal. But also we need the silicon tracker to be lightweight to not interfere so much with the particle trajectory. So typically we use detectors that are made of silicon. And I think some of you actually visited the silicon detector facility that it's down the road 2 weeks ago. And then I think there's going to be another tour for the rest of you next week. So other than momentum that's measured by tracker, we also have the calorimeters that are used to measure the energy of particles. So something that's a bit counterintuitive is that for silicon tracker, we want the tracker to be lightweight to not interfere with the particle momentum. While in this case, we need the calorimeters to be made up of very dense materials. So essentially all the particles that reach the start of the calorimeter will be stopped by the calorimeter. So by stopping the particle and basically absorbing all of the energy of the particle and then measuring the amount of the absorption of the energy, then we're able to measure the particle. So essentially we're destroying this particle and then measuring how much energy it takes to destroy it. And it's similar to like catching a baseball. To be able to catch it, you have to know how much force you're exerting. And by knowing how much force you're exerting, you know the initial velocity and energy of the particle. Okay, so basically I mentioned that the calorimeters destroy all the particles, but there's one exception. So essentially the calorimeters destroy all of the known standard model particles except for muons. So muons are a type of particles that interact very little with most materials. So it would interact very little with the tracker, with the calorimeter. So these will be the only particles that will go past the calorimeter. So which is why we build the muon system at the very end, where we only expect muons to reach the muon system. And they're very, the muon system are very similar to the tracker. They're also made up of several layers. And then we intercept basically the trajectory of the muons to register the hits and connecting the dots from the muon system to the tracker to be able to measure the momentum of the muons. So here you can see a diagram of the CMS detector, and the red line here corresponds to a signature from the muon where it would register hits in the tracker in the middle and, and also register hits in the muon system. So by connecting all the dots here, we're able to measure the momentum of muons with very good precision. Yeah.
Why do muons just go straight on like send like a neutron sun that gets affected by the magnetic field?
Yeah, so muons also do get deflected by a magnetic field because they also have charges. So the fact that you see a very, very straight line here actually indicates that this muon has a very high momentum. So if the muons have, let's say, energy of about hundreds of GeV, then they're barely deflected by the magnetic field. But if it only has an energy of about 10 GeV, you'll actually see that that curls in the detector.
So then why do muons at that high momentum not get affected, like barely get affected by the magnet compared to something like neutron? that even like at 99.99% speed of light, they're still got
Oh, wait, so you're asking about why we're able to guide the protons in the LHC even though it has
it's high speeds, but then you can't guide it.
Yeah, so the magnetic field strength is a bit different. So for example, in CMS, the magnetic field strength is only 3.8 Tesla, while in the LHC is a lot higher. So, and also, which is one of the, and also the scale is a little bit different. So in the LHC, we're able to guide them. But if you remember, the circumference of the LHC is 27 kilometers. So we are able to guide them, but the radius is huge. While in this case, the CMS diameter is only about 15 meters. So we're looking at different scales here. We're able to guide them, but the radius is very different. Yeah.
How do you reconstruct an initial velocity from the collision into the crystal?
For the calorimeters?
Yeah.
So we don't measure the velocity directly. So we only measure the energy of the particles.
And how would you measure it? How would you understand that from the calorimeter?
So I guess, yeah, something that didn't go into details is basically, for example, for our calorimeters, for one of our calorimeters, we use very dense crystals. They're made of these materials called scintillating materials. So the particles will come in with a certain energy. They will get stopped by these materials because of the denseness. And these scintillating materials will basically glow. It will emit photons that is proportional, or the number of photons will be proportional to the incoming energy of the particles, or the amount of energy that's absorbed by the crystals. And by counting basically the number of photons that are emitted in the scintillator, then we can measure the energy of the incoming particle. But yeah, great question. Anything else? I don't know if you can see questions on Zoom. Okay. So yeah, so now I just want to put everything together to give you a more holistic view of things. So move the bars. Okay, so overall, the CMS, I think something that I didn't mention is the scale of things, which may have confused you guys a little bit. So the CMS, here's like a cross-sectional view or the transverse plane view of the CMS. So it essentially has a diameter of about 15 meters, and the length of the cylinder is about 20 meters. And so if we look at, for example, one slice of the detector here, which is blown up, is a blown up version of this diagram here. And here is the collision point, and from left to right, we're essentially going radially outward. So we have the tracker in the middle, which is the innermost tracker, innermost subdetector, which basically detects the trajectory of any charged particle. And then we have the calorimeters. Something that I didn't mention is we actually have two separate calorimeters. We have the electromagnetic calorimeter that mostly interacts with particles that interact through electromagnetic force, so namely just electron and photons. So it will only destroy or stop electron and photons in the EM calorimeter. And then behind that, we have the Hadron calorimeter. So it basically interacts with anything that interacts through the strong force, or QCD, so it basically stops any charged or neutral hadrons. And then we have the solenoid, or the end of the solenoid behind the calorimeter, which essentially provides a uniform B field in all of these regions here, a 4 Tesla B field. And then behind the solenoid, essentially, as you can see, only muons are able to propagate through and are detected by the muon system. So in this little diagram, you can see that the muon is curved a little bit, but this is just the conceptual view of the muon, but this is the typical, I guess, trajectory of the muons that we expect. So one last thing I want to talk about our detector is actually the amount of data that is produced at the LHC, which is a huge amount of data and way too much data than we can ever save. So if we don't, so we save every single collision, which happens at every 25 nanosecond, and we save all the raw data that comes in from all the channels, then we're essentially looking at 1 petabyte of data every single second during the peak operation of the LHC. So it is impossible to save that much of data. So we make use of this filtering scheme, which we filter our events down to about a few gigabytes per second. So essentially we have an online trigger system, which for every event, it will very quickly decide whether this event is interesting, whether I want to save this event, and then it will essentially only save 1 in a million collisions. So even with that, if you compare to the amount of data that's saved by TikTok or Instagram, that's about 10 terabyte of data per day from the users. We're looking at essentially comparable and more data compared to TikTok and Instagram. Yeah.
For the trigger system that automatically sorts it, does it have like a system where it's like it accidentally deletes something that's crucial data? Like, does it have like the history section, see the good stuff? I don't know.
Yeah, so for these online triggering systems, they of course have been simulated before we deploy them online. But for these online triggering systems, once they decide that this event is not interested, then it's deleted forever. But once these triggering systems decide that this is an interesting event, we make multiple copies of this event. For example, we'll back it up in tape, and then 1 copy will go through the full reconstruction chain. So once we decide that this event is interesting, they'll get backed up with multiple copies. But if this online triggering system says this event is not interesting, then it gets thrown away and not recoverable. Yeah.
How does the triggering system decide if an event is interesting or not interesting?
Yeah, that's a good question. So the trigger system actually consists of hundreds of different paths or different decisions. So for example, it really depends on the physics that we're interested in. So for example, for searches that or analyses that are interested in looking for the Higgs boson, we'll look for, which I'll actually talk about, which decays into, for example, photons. Then we'll check in this event if there are energetic photons that may indicate this is an event of interest. Then we'll keep this event. So usually, most of the events that we see in CMS and LHC, the events don't have anything energetic, so we usually throw these away. But if these events, for example, have an energetic muon or an energetic electron, then we choose to save them. But for the trigger system, we try to design a trigger menu that basically casts a white net. Yeah, because we basically know that once you decide that this event is not interesting, then it gets thrown away forever. Yeah.
Is there a minuscule but theoretical chance that there's some particle that's been, unconceived of that is a result of a collision that would get theoretically deleted by the trigger system?
Yes, it's possible. So there are new developments actually on that. For example, using machine learning algorithms to develop algorithms that don't really have a particular benchmark model in mind. So for example, SUSY models or dark matter model, but we just look for anomalies that are different from the standard model. So then in this case, you might not have a particular benchmark or like a known unknown particles that we're looking for. We basically just look for anomalies that are different from the standard models. But yeah, these are very good questions. Okay, so in the next, I guess, section, I'll talk about how we can use the simplified detector that we just talked about to be able to reconstruct the Higgs boson, and also how we discovered the Higgs boson initially in 2012. So I mentioned before that the Higgs boson have very, very short lifetime. So they will decay immediately before even reaching the first layer of our detector. So the only way that we can detect or indirectly detect the Higgs boson is to detect the decay particles of the Higgs boson. And from the Center model, we know, so here's a pie chart of the probability of the Higgs boson decaying to other Center model particles. And you can see this pie chart, the Higgs decays mostly to B quarks. It can also decay to W bosons, tau leptons, Zs, charm, and photons. It essentially interact with every single particle that we know of in the Center model. But maybe counterintuitively, the two channels that give us the most sensitivity and the two channels that we actually use to discover the Higgs boson is actually these two channels that have very small probability. And that's mostly because the signatures that we get out of these smaller channels are more distinct from, for example, Center model background. And so the one channel that we're looking for is Higgs decaying to a pair of Zs. And then both of the Zs will decay to 2 muons. So in the end, we're basically seeing Higgs decaying to 4 muons. And we're really good at, in CMS, we're really good at detecting muons. And we're also good at detecting photons. So essentially the two final states that contain only muons and photons actually stand out and are actually the golden channel that we used at the end to discover the Higgs. So I'll show you an example of how we actually use these decay modes to detect the Higgs. So I'll use the simpler one, Higgs to diphotons, since there are only two outgoing particles. So basically, since we cannot detect the Higgs, we are only able to detect the diphotons at the end. But by measuring the energy of the two photons precisely, so E1 and E2 in this formula, and also the angle between the two photons, the theta here, then we can reconstruct and calculate the mass of the two photon system. And if the two photons truly came from the decay of the Higgs, then we should see that the calculated mass should be close to 125 GeV, which is the predicted Higgs mass. But of course, it's never perfect because our detector is not perfect. Yeah.
Is the theta value often consistent or not?
Often, sorry, what?
Consistent, like.
What do you mean by consistent?
Is it just like at the angle they split off at, like, I don't know, I don't really know where that's at.
I guess it's never the same, if that's what you're asking. It depends a lot, for example, on the initial energy of the Higgs, the initial PT of the Higgs. So it's not going to be the same, but it's correlated with also the energy of the outgoing photons. So if you take all three things into account, you'll always get the rest mass of the Higgs. So yeah, so from this equation, you can calculate basically the invariant mass of the two photon system. And if you plot, essentially, if we collect a large number of events, and then we just plot this quantity from that we get out of all of our collision, then for things that don't come from the Higgs boson, we would expect a relatively flat distribution. But if the photons do come from the Higgs, we'll see a little peak at 125 GeV. And as I mentioned, it's never going to be exactly at 125. We'll always see some sort of distribution due to the resolution of our detector. So in 2012, the CMS and ATLAS experiment discovered the Higgs independently. And here you can see the real data from ATLAS in 2012, where we saw a little bump here, 125 GeV. It's a bit hard to see given the large number of background, but here, if you can see the excess of data with respect to the background model, then you can see that we clearly see a bump of the Higgs boson. And so, and Peter Higgs, who the Higgs boson was named after, was awarded the Nobel Prize in 2013 for predicting the existence of the Higgs boson. So yeah, so I just have a short slide of what's next for the LHC community. The LHC community is preparing for an upgrade in the next few years that would actually allow us to take data even faster at about 7 times the speed that we're currently taking data today. We're gonna, and overall we'll be able to take 20 times more data by 2040. And currently we're upgrading both the Atlas and CMS detectors to be able to cope with this higher flux of particles. And some of you have visited the silicon detector facility where Fermilab is responsible for upgrading the silicon tracker in CMS. And this larger amount of data will allow us to measure the Higgs boson properties more precisely and also discover more unknown particles. And there's a lot ahead of us with very exciting future. Thank you. So any more questions?
Yes, and if you're online, feel free to put questions in the chat. But I'll look around for a hand. Get you the microphone.
Because the Higgs boson, it decays really quickly, can we just make a super small ring to detect it, or are we just working with the decay?
I think it would be too small for, given our current, for example, position resolution. Like the position, I guess I don't know what the unit in micrometer would translate to for the Higgs decay length, but the current, for example, the position resolution of the tracker is on the order of 10 micrometer. It would be too small for us to actually be able to detect the displaced vertex.
What module does the CERN use to store the data? Like a solid state driver or something like that. How does it store the data?
Yeah, some of them are stored on tape. So for example, the raw data that we don't usually use as backup, we will use tape, and others we have basically data center around the world. So we store multiple copies of our data around the world, and also it makes it easier for us. For example, at Fermilab, we can use the data center at Fermilab to access the data. But if you're in Europe, you don't really have to ask Fermilab to transfer the data over. They also have their own data center in Europe to access the data easier.
Do y'all know what Christina means by tape? You're all maybe too young to remember a cassette tape, but it's well, it's not ancient technology, but we still use that Fermilab. It's a very cheap way and very reliable way to store data, but it's just, I don't know, how does it work? There's, magnets, or you can set zeros and ones on a physical string of tape. They used to use it to encode music, but we use it to encode physics data, and it's very stable. You don't have to worry about it crashing like the spinning hard drives do. Let me check on Zoom. Any other questions? So there is one. If the plan is to collect more data, I mean, whether it's higher intensity or, it's a longer run, how will the trigger system have to adjust to this larger flux?
Yeah, that's a great question. So we are also upgrading our trigger system to be able to cope with this larger flux and also be able to accept more data. So we will be able to accept 10 times, well, we'll be able to collide 10 times faster. We'll also be able to collect 10 times more events at the end of the day.
I guess, could you maybe talk a little about the difference between high intensity and luminosity? I don't know.
It's the same.
The same.
Yeah.
Okay. I guess there's energy and luminosity are the two that I'm thinking.
Yeah, so energy is different from higher luminosity, but higher intensity is the same as higher luminosity. So if you, for example, if we increase Yeah, I guess if you increase the energy, it would change, for example, the probability of, for example, producing a Higgs out of protons. So I guess the final number of Higgs boson that we get out of the collisions is kind of like the product of higher energy and higher luminosity. So both would increase the number of Higgs boson that we get at the end. But the higher luminosity essentially tells us how many collisions we have or how many events we get per collision. But it doesn't tell us, given a collision, what's the probability that we get a Higgs boson out of it. I don't know if that makes sense.
Have we confirmed that this is the Higgs boson, or is this the Higgs-like boson?
That's a good question. So I would say, so let me go back to the pie chart. So there are many properties that we predict in the standard model about the Higgs boson. So for example, the mass, or we don't predict the mass, but this probability of decay is predicted by the standard model. And so essentially, the first two channels that we have detected are these two channels. And over the past 10 years, we're able to detect all of these additional channels. And the branching ratio does agree with what's predicted in the standard model. But there is still, for example, a small probability. So for example, Higgs to CC hasn't been detected. There are also a probability that Higgs decay to invisible things. So there are still a few, I guess, smaller slices in the pie chart that we haven't explicitly confirmed yet. But most of these bigger things have been confirmed. So it's still mostly a standard model Higgs, but yeah.
When you talk about the products of like a Higgs decay, what's a jet like on the slide?
Oh yeah. So a jet is what's a good way to describe it? So I guess you heard from the previous talk that quarks and gluons don't like to be alone. So essentially, once they're produced, they will basically pull another quark or gluon out of vacuum, and they'll get bunched together to basically produce a spray of hadrons. So you could think of it as basically a bunch of hadrons that are bunched together.
I guess looking at this pie chart, for instance, so one question from Zoom is, how do you predict which decay particles are produced by fast decaying particles like the Higgs boson?
Wait, by what? Sorry.
Like, how do you predict which decay particles are produced in the decay? Like, how do you know which, the pie chart and the percent of the branching fraction? That come from theory or from?
Yeah, it mostly comes from theory. I guess we do know that the Higgs likes to couple to heavier objects. So for example, it's more likely that the Higgs couple to B quarks. But yeah, all of this, I guess, comes from theory, if that's the question.
Probably time for one more.
Could you theoretically speed a particle like fast enough for the Higgs boson to reach a detector?
You mean make it
For
faster
decays?
or?
Yeah, I guess. I don't know.
I guess not at the energy level that we're in. So for example, the Higgs that we produce at the LHC are not, of course, or they're mostly at rest, but there are some that are energetic. But even for these energetic ones, they're still not enough to be able to reach the first layer of the arbor detector.
Anything else? Not, let's thank Christina. And maybe we will take, I don't know, anyone need bio break, bathroom break? Just a couple minutes? What do you think? Or, yeah, let's take 5 minutes. We'll get set up for the tour and then we'll be started at 11:05 sharp in Chicago time. And yeah, for people on Zoom, the tour will, please sit tight because the tour will be online and they're pulling it up right now. All right, it is 5 after the hour. so hopefully that break was rejuvenating. But yeah, we're very fortunate to have folks out in Europe in the CMS control room here to talk to you all, get a tour of CMS, the experiment we we're just hearing about. One of the experiments that discovered the Higgs boson for the first time. So yeah, we'll take it away. We're excited to hear what you have to share with us.
Okay, hi everyone. So we can, I think, go ahead and get started. So I just very quickly wanted to introduce myself and my colleagues here. So my name is Andres. I'm a scientist based at CMS.
My name is Derek, also a scientist based at CMS.
And we have a few people who will join us today for the visit. I assume at some point you'll see them on camera. But yeah, we also have our technical team. Zoltan is here and Noemi. And then we'll have Peter. I think we're getting ready.
Peter,
This is
Carla.
Peter and Carla. And yep, so we will send, if you want to say a word, go for it. And we will send them downstairs to the detector area. And this is going to be really cool because we're going to be able to show you guys the actual CMS detector. And we are commissioning the magnet. So we'll talk about that a bit and we'll demonstrate what what the environment looks like downstairs with the magnet at half field, just about. So we're still bringing the magnet up or ramping it up, let's say. So it's at 2 Tesla out of 3.8. And yeah, so I think we can start with a quick introduction while our colleagues are getting ready. So let's just show you guys this picture. I'm sure you either saw it in one of the talks or you have seen a similar picture before. So this is a representation of the LHC in the area where we are. So this is just outside of Geneva, Switzerland. And yeah, you can see the Geneva Lake. And then you can, if you squint a little bit, you can see the airport and you can see the Alps in the distance. Today was an especially nice view. It's getting dark now, but yeah, on a nice day, you get a very nice view of the Alps on the way to P5. So we're here where CMS is indicated. And of course, you see the representation of the LHC ring. So there's no orange line painted through the countryside. It's, of course, just showing you where the underground areas are. And as you can see, this is 27 kilometers in circumference. That's about 17 miles, I think. And you can see where the CERN, the main site, is about 20 minutes from Geneva, and then we're about 15 to 20 minutes from CERN itself. So I think I will skip this slide. There's some interesting history. CERN was founded 70 years ago, 72 actually. So it dates back to the 1954 is I think when it was established, and we still use some of the accelerators that were commissioned at around that time. So you can see the proton synchrotron, which is very much still in use. It was commissioned in 1959. Yeah, so we'll also be showing you a few images from the control room. We also have some in-person visitors here. And yeah, okay, so I mentioned that most of some of the facilities are underground. So you can see here a picture of the LHC underground areas. And there are 8 points, we call them interaction. Well, there are 8 points around the LHC, and point 1 is where Atlas is, point 2 is where Alice is. I'll talk a little bit in just a second about Alice. Then we have CMS at point 5, and then LHCb at point 8. And so these are the main detectors that we have around the LHC. We have Atlas and CMS, and Atlas and CMS are the most general purpose detectors that we have at the LHC. So that means that we have similar physics goals. We study the same kind of processes and We sort of compete with each other to try to get the best results and also get them faster than the other collaboration. And we have LHCb, which is a smaller detector, which focuses on what we call flavor physics. And then we have the ELISE experiment that focuses on heavy ion. So let me switch to Derek, and maybe they can describe what they're up to right now.
Hey, so if you can hear me, we're about to go through one of the safety doors here at CMS. And so basically, when you're entering a radiation zone, which there's no radiation right now because we've been shut off and it's very safe, but it's a protected area, you have to have one of these, a dosimeter, and it's linked to my biometrics, my actual retina in my eye. So I first have to scan to go into this room, which it will then close both doors and trap me inside. And then it has to scan my eyes. So let's see. First it will, hopefully. And now here I look into this box and it scanned my eyes and it allows me through once it all matches up. Now Naomi will do the same. And she'll give you kind of a view of inside this. She has to smuggle the camera, actually. So this little box, it actually scans your body and tries to make sure you're not smuggling any tools or perhaps another person in with you. So she got through. She's very good at smuggling. But now we're going to ride the elevator down. We can give it back to you, Andreas, because we usually lose internet about this time. But we'll go 100 meters underground.
All right, see you downstairs. Okay, so I wanted to very quickly just show you guys a little bit, just discuss a little bit of the CMS detector, which again, you may have already heard a little bit about CMS. So I'll be very brief. I think what you can say about CMS, if you don't have a lot of time, is that it's a very dense detector. So CMS is about twice as heavy as the Eiffel Tower. And even though it's significantly smaller than the Atlas detector, it is twice as heavy as the Atlas detector. So it's we say that it's compact. So of course, it's not small, and you'll see really how big this detector is compared to our colleagues just in a few minutes. But it's 50 meters tall. And as I said, it's very heavy. So one of the central features of the CMS detector, it's the magnet. And again, we'll discuss the magnet and you'll see the effects of the magnetic field. But this magnet is inside of CMS. So you can hopefully see that there's this cylinder, a white cylinder that I'm indicating with the mouse here. And that's a huge superconducting magnet. So we have to cool this down to 4 Kelvin or so. And this, when it's under those conditions, this huge magnet, which is 6 meters in inner diameter and about 10 meters long, it will generate an immense magnetic field, which we then use to look at the trajectory of charged particles. So these charged particles will bend under a magnetic field, and we can deduce or measure the momentum of the particles from the curvature of their trajectories. And around this magnet, you can see that there's lots of red plates. So that corresponds to steel. That is 12,500 tons of steel. That's what we refer to as the return yoke. And this contributes to the magnetic field outside of the magnet. So inside of the magnet, we have a very concentrated 3.8 Tesla. Outside of the magnet, generally the field lines would dissipate or propagate very quickly. So all the steel works in such a way that it sort of concentrates the magnetic field lines, and it allows us to still generate 3.8 Tesla when we circulate 18,000 amperes of current through it, which is not quite the case today. We don't have the magnet at full field. We have only 2 Tesla. And as I said, this is part of the commissioning of the magnet, since we're coming back from the year-end technical stop. So we don't operate the LHCs during the Christmas months, let's say. So typically by early December, the LHC is no longer in operation, and it typically comes back around March. This is an especially short break, let's say, for the winter months. And we're actually already expecting the first beams as early as the 21st, I think, of February, so later this month. And that means that we already have CMS basically in its configuration ready to take data, ready to observe these collisions. And so that also means that we're commissioning the magnet, and on Monday we will finish the ramp up of the magnet, but for now you'll see the effect of only 2 Tesla. So something that's also interesting is our colleagues are walking through this sort of labyrinth, and there's a very thick wall that separates the detector from what we call the service cavern. So they're making their way now to the floor of the experiment. And so I think I can already hand it to Derek, so you can guide us into the detector. Looks like they're still muted.
He needs to unmute.
Okay, sorry. We have to switch our gear here because once we're inside, the magnetic field actually affects our gimbal, which keeps our camera steady. So we have to switch to a more manual system here. But as Andreas said, we're right outside of the CMS detector. And to get into this area, not only did we have to scan our dosimeter again and do the biometrics, but we had to take a key. So every person that enters this area has to take one of these keys. And basically, you cannot actually turn on the LHC until all of these keys are returned. So the proton beam for all the experiments cannot be turned on until there's a physical verification that everybody that went into the experimental chamber has also come out and brought their key and put it back into the holding device, basically. So another very high-tech security system that we have here, but for good measure. So we also have our other 2 crewmates coming with us now. But if we're switched, do we go in? Okay, one more moment. But once we're inside, we're going to see some of the effects of this field. So I'll be honest, I wasn't able to keep up with exactly what Andreas was saying because we lost some internet. But the point of having this very strong magnetic field is that it curves these charged particles or particle collisions, and then that allows us to measure their momentum. So the magnetic field is very strong, and we're going to see some of these effects with some magnetic materials just on the other side.
So we don't see your video at the
Yes.
moment. Maybe we can actually share the screen very quickly so I can show the
Go ahead and-
participants what these tracks will look like. So I mentioned that under a magnetic field, a charged particle will bend. And as you might imagine, the higher the energy or momentum of the particle, the straighter the particle will go. It's a particle with high momentum is more difficult to change its direction. So it will not curve as much. So that's how we can measure the momentum of these particles. And then we have multiple layers. So we have multiple layers in our detector that we can use to detect different types of particles. And so this is, of course, a view of a slice of the CMS detector where the particles travel into the page here. And you can see that different particles are produced from those collisions. And you can see where the magnet is here, the superconducting solenoid. So I think the most striking here is in blue, we have a muon. Muons are heavy electrons, essentially. So they're just like electrons, but they're 200 times heavier. And then
Am I muted?
You're not muted, but if you want to jump in, feel free. And yes, we have this muon, again, where you can see it's bending under the magnetic field, but then after it exits the magnet, then it bends in the other direction. That's because the orientation of the field lines is opposite inside and outside the magnet. And then you can see that there's other particles that are produced and they are, let's say, trapped or they are absorbed by different parts of the detectors. So we have an electromagnetic and hadronic calorimeter, and that's the way they work is they basically absorb these particles and a shower is produced. And we typically have materials that we call scintillators, which produce light that is proportional to the energy of these particles. And then inside of that, we have what we call the silicon tracker or the inner detector. And these are many millions of channels of silicon sensors. So these are in a sense similar to a camera sensor, but we're measuring charged particles when they pass through through the material. We can get a signal, and then we can essentially connect the dots from anywhere that we get these signals and then reconstruct the trajectory of these particles. So that's in as quickly as I can make it sort of an overview of how we reconstruct different types of particles. And then I won't go into too much more detail, but depending on where you see a signal, for example, if you see a signal in the electromagnetic calorimeter versus the hadronic calorimeter, that will tell you the type of particle, the composition of the particle, right? So if it's a photon or an electron, or if it's a hadron, which is a particle that's made up of quarks, like a proton or a neutron, or many other types of particles. So maybe we can check with Derek.
Yes.
I think they are ready to go, so we can switch to them.
Yes, can you hear me?
We can hear you, but we lost the video.
Sure. So Naomi is working as hard as she can to try and get our video back. But also, for the people watching this, all of these virtual tours really are done by physicists. And although we figured out our production very well, here we go. So we have to use the front viewing camera, but I think it at least works. So as you can see behind me, this is the CMS detector. Maybe I can even take it. I'm like a vlogger holding. So we have the CMS detector. And in all those pictures that Andreas had shown you, this is the outer edge, basically. So this is a big piece of steel. It's steel, right?
Yeah.
And then just on the other side of this would be some of the muon detectors, but then also it has this cylindrical shape to it, as he showed you, many, many layers. So we're going to kind of walk. Yes, all those layers. So you see.
Yeah, so you're basically looking at this plate here. This we call the end cap plate.
Yes.
And in fact, you can see, I mean, I can even point out, you see these these yellow supports. So those correspond to these yellow supports over here. And yeah, that's basically the HF platform on top of that, the hadronic forward.
So if you can see our view, what we brought down with us, that's a good spot right there, is some magnetic chain. And we're hoping that as we walk, closer towards the detector in the 2 Tesla field, we will see some effect. Now I can already see a little bit of an effect if I can get it to be still. And in fact, maybe if you come over here from the side. So this magnetic chain, it's going to try to align itself with the direction of the field. In whichever direction that's pointing, I can't tell you, but we can look at the chain and kind of deduce what direction the field's in. So now I'm going to walk a bit closer to CMS, and we'll see if this starts to bend more. Now, Andreas told you the magnet's at about half strength right now, but even so, here we are near right underneath. And if I walk over here, now the chain is really, right there. Wow, okay. So now it's really, really bending. And if we come back here next week, we would see even more of an effect. But I think you get the point that this is quite a strong magnetic field that we have in this room. Well, oof. And so here's some of the steel. And of course, that's going to be magnetized in this Tesla field. So maybe I can even do something like this. Yeah. So can you tell what direction, at least coming out of this piece of steel, the field is pointing? You can see it here.
Yeah, so we forgot to introduce our other colleague. So you have our rubber ducky colleague who's attached to a paper clip. So that's why the rubber ducky is also attracted to the piece of steel.
It's quite hard to explain how it feels. In fact, now I'm holding a piece of, a metal tool, and this is very, it's very strange. This is my first time being in the experimental chamber while the magnet's on. So this is just I'm forgetting the name. This is a tool, a wrench. And since it has some length to it, it wants to align itself with the field, and you can kind of see that it's done that here. I'm really not holding it in this orientation. I'm just kind of moving my hand around it, but I'm going to slowly turn it. And at some point here, it's about perpendicular to the field. I can really feel this resistance. It'll snap. So it's always wanting to align with the direction of this field. And that's just crazy. Even if I hold it like this, there, you can, I proved it. Okay. I'm not holding, I'm not forcing it in this direction. So yeah,
Magic.
it's very, very strange sensation, but also a bit familiar when you play with like neodymium magnets. You kind of know what it feels like, right? But now this is like really ramped up to a whole nother level. So let's look at our chain here again. I don't know if you could see that too well, but it's just floating here in space. We got to find the angle. We're really struggling with this front camera a bit, but. And I can just kind of pull it off. Wow. So if I do this, and we'll see it kind of do this weird stuff in the field, no? Wow, very cool. Should we move somewhere else? All right, Andreas, if there's anything else you wanted to say, we're going to move to a different part of the chamber now.
Okay, so maybe I'll just quickly mention something about CMS, which you might not appreciate directly, but something that's very central to the design of CMS is that it is modular. So it's this cylindrical object, but it's cut up into about a dozen slices. And as Noemi's going by, I don't know if she can hear me, but she may be able to show the gaps in between the slices.
Can we show some of these gaps?
Yeah, and you can see here what I mean by one of these slices. You literally take this cylindrical onion and you chop it up into about a dozen slices. And so we have each of these is slightly different, but they're symmetric around the well, from one side to the other, let's say, and typically they're also radially symmetric. And also here you can appreciate how many cables are involved. So some of these might be high voltage, especially the red cables are typically high voltage, and you might have these blue cables, they could be low voltage. And yes, a lot of infrastructure required. So the point of slicing up the detector was, again, to make it modular, and that makes the construction of the detector and the installation of the detector easier. So CMS was actually assembled on the surface, and each of these slices was craned down one at a time. The alternative is to bring everything down gradually and then assemble it already downstairs. So this was designed in such was designed to be modular, which also helped us to assemble it on the surface and test everything before it was craned down. And then another point of having it be modular like this is in this kind of a period where we don't have collisions, we can actually open up the CMS detector. So we, these yellow supports that I mentioned, that gets craned to the surface, and the HF, the hydronic forward section gets put in that garage. I don't know if you can appreciate the garage with the yellow doors. And then you can move the slices. You can move them using some crane, we actually
Maybe
have
we can show the hole.
Metal.
So if we show the hole, sorry, can you hear us?
Yeah, go ahead.
Well, that's you're mentioning the crane or a crane. I'm not sure if we can see it too well in the video. Yeah. So this is basically the hole that CMS was lowered down, the slices that Andreas was talking about. And so there is a crane all the way up there at the surface. But then if you're down here while they're doing maintenance, you actually, they're driving it around here, but it's actually controlling the crane over 100 meters up on the ceiling of the building overhead. So this is where CMS came from, basically, in pieces. And then we slid the slices that they showed you, into this room, basically, to fill up the and build the whole detector. We can see the feet, right? That's how we move the slices, kind of scoot them around by rotating those feet.
Yeah.
And I believe
so
they use high pressure air. Yeah.
yes. So these are what we call air pads, and
Mhm.
I don't recall. It's maybe like 50 bars of pressure or something like that.
Oh, wow.
Quite a huge.
Yeah, quite a large amount. And so these are actually what we use. So you can see that there are metal cables here, and this will actually pull on the slices when we need to move them. We also have to grease the floor, so it's a complicated maneuver, and it takes a lot of planning to organize this. But these are the actual metal cables that we use to move the slices.
Indeed, that's a hovercraft.
Yes, exactly. So it will actually lift the slices. These slices
Yeah.
are really heavy. So I think on the order of 300 tons for the least heavy. Yeah, so I did have one question that maybe you can help us answer, Derek. So,
Yeah.
so one of the participants asks if the magnets are strong enough to accelerate particles. Why isn't Derek zooming around?
Why aren't they zooming around right now?
Why aren't you zooming around?
Ah. Well, magnetic fields, if you take a physics class with electricity and magnetism, you will learn very quickly that magnetic fields only affect particles that have charge. Okay. Or you could say things with charge. If you want to have some metal ball with a lot of electric charge, it would also affect that and could deflect it, I suppose. Why I'm not zooming around or being deflected is that my body, everything I'm made out of, is electrically neutral. I have equal parts protons, equal parts electrons, or at least I hope, but I'm neutral in charge. And so I don't feel the effects of the magnetic field. But other things that either have an electric charge, or if they have a magnetic moment or some if they could be affected by a magnetic field by having their own internal magnetic field, like pieces of iron, atoms of iron, then these could also feel a magnetic field and try to align with it. But
Yeah,
yeah,
so
since I don't, go ahead.
yeah, I was just gonna add, I mean, without going too much detail, when you have metals typically are the electrons in the metal they can move around in the material, so then that makes them susceptible to the magnetic fields. So we had sort of a follow-up question I think is very interesting. So it's asking about the instruments that we have in the cavern and how we eliminate any interference, or does the magnet affect the instruments inside the detector? And so there's lots of different layers and types of detectors. So I mentioned these calorimeters with scintillators, and I also mentioned the inner detector, which is made up of a lot of silicon detectors, silicon sensors. And so you very much have to design these components, these instruments to operate under these magnetic fields. And in fact, you can sort of leverage the magnetic field for some parts of the design. So in the silicon sensors, we can actually work or design the instrument so that we orient it in a way that we can use the magnetic field to have what we call charge sharing, and there's something called the Lorentz angle. So this is a bit more technical, but indeed, this all has to be considered, and there's lots of custom electronics that are designed to operate in these very large magnetic fields. And keep in mind that the magnetic field that you are now observing the effects of is still much smaller than the magnetic field inside the magnet itself. So we talked about 2 Tesla, but that's the magnetic field inside the solenoid, which we cannot access. We would need to open up CMS for that. And then outside the magnet, the magnetic field within the steel itself is quite strong, but it quickly dies out as you move away from the detector. And you could see this when Derek was approaching, how these chains were responding. So the closer you are, the stronger the effect. And of course,
We can
inside
actually,
magnets.
yeah, we can actually demonstrate that for you. So if I, allow it to curve like this, and now Naomi and I will just walk directly away from the detector, and we'll try to see how this chain, I hope it's visible. But we'll see. By now, it's pretty straight. And especially by now, it's, I can see a little curve, but it's very straight. And all I took was maybe 10 steps from the detector, right? So magnetic fields, they drop off very quickly with the distance that you move away from them. And yeah, as Andreas was saying, it's a very good thing to keep in mind. It's this strong right at the edge of the detector, but remember how strong it must be at the very center where we have our collisions. So that was a very good point. I'll walk back.
So I also wanted to mention something really quick. So we're in the control room and we have the shift crew here. So while you were talking, Derek, I don't know if anybody in the audience noticed that we had a bit of music. So that was a song by Sheryl Crow. And so as we speak, and as Derek and our colleagues are down in the cavern, we are actually we are running the detector and we're collecting data. However, as we've mentioned several times, we don't have a proton beam going through right now, of course, but we can, in fact, look at muons that are produced in the atmosphere from incoming cosmic rays. And these muons, again, they're 200 times heavier than an electron. That means that they can punch through the Earth. And we can see these muons traveling through our detector as we speak, right? So there's muons that are being produced, again, from cosmic rays hitting the atmosphere. And these are going through the detector. And we actually use this data for alignment purposes of our detector. So as we speak, we're actually collecting data from, and it's, again, part of the commissioning process to get the detector in shape and ready for collisions. Okay, so there's a couple of cool things as you guys go upstairs. Maybe we can show the forward shielding here.
Yes.
So this orange block over here is part of the forward shielding. And in fact, this is the new forward shielding, which is reinforcing the original forward shielding. And these blocks, so they're there to sort of protect the experiment. So you can see this orange tube here. That's the original shielding. It doesn't show you the new forward shielding, which goes around this. And so part of why we need this is because when we have collisions in the center of our detector, we have to focus these protons, these charged particles. And so when you accelerate or you change the direction of a charged particle, and when these particles are traveling at essentially the speed of light, we say they're relativistic particles, then you will have, they will produce a type of radiation. We call this synchrotron radiation. And so if you don't shield your detector from that incoming radiation, when you, again, when you bend or you focus these protons, then that radiation is hitting your detector and that you can consider interference. So that's a big part of the reason why you have this shielding in place. And yeah, Derek, we can maybe hand it to you and you can show us around the CMS detector.
So we're going up, another one. We're going up to basically be near the top of the detector. Blockhouse. Sorry. So as we arrive up here, we can get kind of a top-down view. And I guess our hope is that as we move around the experimental chamber, we hope it really conveys the size of how big this thing is, our detector. Even though it has the name the compact muon solenoid, it's still quite a large device. It's only compact relative to Atlas or some of these other large detectors, although Atlas is, I believe, the largest. So we're compact relative to Atlas, but still 5-ish stories tall. So from up here, we can see a lot more of the forward absorber that we were talking about, the orange. And that kind of, as Andreas says, covers the beam pipe and really tries to absorb any external up the pipe collisions that may happen by accident. And we're just trying to filter out things that might cause fakes, you know, or background noise in the detector. If we go over here, maybe we can see. Also, there's an interesting thing I'd like to point out here. We can see them. These red, yeah, where's my hand? These red things along the ceiling. You can see them up there. But this is one of the safety, another safety device in the experimental cavern. If there were to be a fire or something while we're running, these red devices are able to actually eject a foam that would completely flood this cavern, but extinguish the fire, and thus hopefully save some of the detector. And you can't really have a fire brigade coming down here to put out a fire. So this is our solution for that. Why don't we try to?
So it's a last resort, however. So there's there's fire suppression system is quite sophisticated. So there's at least 5 stages or systems that we can use to react to a fire. And this flooding of the cavern, it happens very quickly, and it is not good. So it's a last resort.
No.
But if if your detector is on fire, then that's a bad situation anyway.
Yeah.
And it's only been used, I think, once for testing. So it of course, we've been fortunate that we never had a situation in which we needed to use it. But again, it's part of the safety systems. And there's many safety systems. I mean, we're talking about a fire here, but there's many types of situations you can have. So we work with cryogenics. So if there's a leak with cryogenics, that implies that the level of oxygen in the air will be reduced around that leak. So basically this cryogenic gas will displace the oxygen. There's any number of possible situations. So the safety, actually, both for humans and also for the detector itself, is a huge part of the complexity and the emphasis when we have these very large detectors. So it's a very sophisticated safety system, again, both for humans and for the detector.
So while we're doing collisions, basically, this chamber, and this is also why you have to have a dosimeter to be in this room, but this chamber does become irradiated from the outward coming radiation from the collisions. And so this is always on the mind of people that are designing safety systems or stuff that any work that has to be done in this room, right? Because basically, when we shut off, as we're doing the collisions, when we shut off for a moment in time, there's an opportunity to come in here and replace some parts or do some work. But there is that residual radiation that needs to be tracked and monitored to make sure that you're not receiving too much of a dose. And yeah, in the case of a fire, if it's during collisions, I'm sure we would turn the beam off, but you need something to extinguish the fire right away. And you can't really rely on just sending people in immediately. You need some other system or multiple systems, as Andreas said. So are there any other questions, or is there anything people would like to see while we're down here?
So I don't see any questions, but I would encourage the audience to ask any questions via the Q&A. There's one more.
Including in the room, if people have questions,
So
they can speak up and we'll.
So there's a question about, I don't know if they're trying to speak to us for somebody, but.
Somebody tried to speak to us, but won't hear.
Yeah, well, there's a question about the effects, the physical effects from the accelerator. So whether there's any effect that people can feel from the accelerator. And so again, the accelerator is not running at the moment. So it's a little bit difficult to think of something. I mean, you mentioned the residual radioactivity in the cavern. There are parts of the detector that are much more highly radioactive than others. So where the parts that Derek and our colleagues are accessing right now are not among them. So the inside the forward shielding, so that's one area that's quite radioactive, and inside the inner layers, very close to the beam pipe, in the center of the detector. So you can imagine that where the collisions happen, so that area is much hotter. So that's something that can measure. but it's not something that I think you don't directly feel this, but of course we have to, as
No.
Derek was saying, we have to measure it and
Yeah.
be aware of it, and there are legal limits, right? So it's not just whatever we feel. There's a legal limit for what a dose a person can receive in a year, and we have to, of course, we take that extremely seriously, and um, all of these things also involve training, so you have to train the people that have access to these areas. But I can't think of anything that you would say you can feel from the
No,
effects
I
of it.
can't. I mean, this has nothing to do with us, but an interesting note that's a bit related. Some particle detectors are called Cherenkov detectors. When you have a particle going through the material like water, the particle goes through the material faster than the speed of light can go through that material. It emits this radiation, emits this blue light. I'm saying all of this because astronauts on the space station, I have heard that sometimes when a particle from outer space goes through their eyeball, there's a lot of water in there. It can emit some Cherenkov, and they can actually see a little flash, which would indicate this particle has gone through their eye. That does not happen here. I've never heard of anybody having a particle go through their eye, but when the accelerator's on, nobody's in this room. Nobody is in the tunnel where the beam is.
If it would happen, that would be a problem.
Yeah, exactly.
Yes.
So that would be
So-
a catastrophic failure of the safety systems.
Yes, exactly. On the space station, they can't get away from that radiation. But here, we prevent people from getting into areas where there would be that radiation. So to also answer the question, no, I've never heard of anybody here experiencing any effects of the beam. If they did, that would be probably a bad thing. You know, they hadn't, we hadn't done our
We
proper
try to
safety.
avoid it at any cost.
Oh yeah.
Yes.
We have one question from a student in the room.
Mhm.
Does the temperature inside the CMS exceed the material temperature limit, or like, does it exceed the temperature in which the material would melt? And if so, how do they contain it?
So maybe I can try to answer. I don't know if I fully understood the question, but let me first, if we could share the screen, that would be nice. So I can show you, I showed you this radial slice, or the slice of CMS, and again, the particles are going through the middle, and you can see the magnet and so on. So if you consider, first of all, the protons are traveling in a strong vacuum inside a beam pipe, which is typically a steel tube, but inside in the innermost part of CMS, this beam is made of the material beryllium. Is that right?
Beryllium.
Yes, beryllium. Because of its properties, so it's lightweight, so you want to reduce the interaction of these protons with that material, but it's still strong enough to support its own structure. In any case, when we talk about temperatures, in this innermost layer, the temperature is kept to something like minus 20 degrees, minus 30. And so that is to avoid the degradation of the silicon itself from being exposed to this ionizing radiation. And then we have the electromagnetic field, and that is just, I think, maybe even less, 2 meters from the interaction point. And so already there, you have to keep the temperature at 20 degrees exactly. And that's because I mentioned that we have scintillator material, and the scintillator produces light, but the amount of light that's produced depends on the temperature. It changes with the temperature. So that means that if you don't have a steady temperature, your measurement is going to be inconsistent, which is really something we want to avoid. So that has to operate at exactly 20 degrees, and that means that we need a very sophisticated pumping system. We need to pump water to maintain that at that temperature. So one of the things that happens is there's a lot of electronics, and when you're reading out the data, that will increase the temperature, right? These electronics will get hot when you operate them. So all of that water circulation system is keeping that temperature steady. Same applies to hadronic calorimeter. Well, not exactly the same. It's not as sensitive to temperature, but we keep it at around 20 degrees. And then we have, again, this superconducting solenoid, and that has to run at 4 Tesla, or so, sorry, for Tesla, at 4 Kelvin. And in order for us to keep things insulated from each other, the vessel, so this superconducting magnet sits inside of a vacuum vessel. So it's insulate it from the rest by literally having a vacuum surrounding it. And then after that, we have, again, as a reference point, the magnet is 6 meters in inner diameter. So already in 3 meters, you have all these radical changes in temperature. And then after that, the muon systems are pretty much operating at room temperature. So that gives you an idea of the drastic changes in temperature within the detectors. I think I'm not sure that I'm answering your question exactly, but
I think his question was about from the particle collision and the stuff coming out, does it heat up any of the detectors so much that they would melt? And do we have to keep them cold for that reason? I think that's more along the lines of the question.
That's an interesting question.
That's an interesting question.
Yeah.
Indeed, the energy deposited by these particles in the detector is very small.
Yeah.
And that's the answer. That will not melt anything.
Yeah, but let me maybe go a bit further. So just to really give you a sense, if you take just a proton, right, not even the particles that are produced, but a proton that is traveling essentially at the speed of light. So just to give you a sense of what I mean, this LHC tunnel is 26.6 kilometers in circumference. A proton will circulate this 27 kilometers, 11,245 times per second. So these protons are effectively traveling at the speed of light. But if you look at their kinetic energy, it's comparable to a kinetic energy of a flying mosquito. And that doesn't sound like much, but we're talking about a particle that is like as small as it gets, right? This is extremely small. And in fact, when you take the collective energy of all these protons, we have the protons are kept in bunches, and there are about 160 billion of these protons in a bunch circulating together. And then we have about 2,450 of these protons that typically circulate around the LHC. When you combine all of them, then you're talking about the kinetic energy equivalent of a train going something like 200 kilometers an hour. So that's, I guess, like 120 miles an hour or something like that. Yeah. So the energy of these particles is, on macroscopic terms, if you take an individual particle, is not a very hugely significant, but it is very much quite an well, impressive amount of energy when you take the whole
Actually,
particle.
not the energy of an individual particle is high, but the energy density that we create. In one of the talks right before this visit was a number 10 to the minus 18. That's about the size of this collision volume, you know. So 10 to the minus 18 meters. And if you make the energy density from these values, you get an extremely high value, and that's what we are working.
Yes, absolutely. So all that said, a particle that's produced is not going to have a hugely significant amount of energy enough to raise the temperature significantly. However, there are many ways we can go and discuss this. So you can also consider the LHC dipole magnets. And these are exposed to the synchrotron radiation because these particles are bending. So you can have sort of a secondary effect of the circulating particles hitting that magnet, and that can deposit energy, and that can affect the ability of you maintaining that magnet at superconducting conditions. In other words, this radiation coming from the circulating particles can, in fact, cause what we call a quench. So it can increase the energy enough that very microscopically you get a temperature spike that goes above the critical temperature, and then you lose superconductivity. So that sort of thing can happen. There's other effects that you may have. So you can also liberate electrons in the material and have an electron cloud that also creates problems. So there's many possible situations, right? And many possible effects that a particle at these energies can trigger. But maybe I'll leave it at that and check if there's any other questions or anything, Derek, that you want to add.
Yeah, I want to show CMS.
So I think you're cutting out
That's
quite a
basically-
bit, Derek, unfortunately.
Is this better or
Yeah, it's better now.
still cutting out?
Yeah.
It may be a magnet. I'm not sure. My what I hear gets a little bit crackly when we get close to the magnet, and that would be because speakers actually use an electromagnet to move around a permanent magnet to generate sound. So as I get near this field, yeah, that's going to start affecting what I hear. And I believe a microphone works the same way. So if I get too close to the magnet, it's probably going to affect how I sound. But basically, I was just saying, we came down a level. We're right beside the detector now. And even if my mic cuts out, I'm going to walk towards the detector and we're going to see the field from here, how it changes. Because right here, it's quite crazy.
So as we're watching Derek, I want to again encourage the audience if there's any questions. I think we need to be wrapping up relatively soon, so this is your chance. That looks really cool right now. I don't know if you can see this chain,
crazy.
Almost like
So
a
we have
spring.
some questions in the room. Passing to one now.
So even though water is slightly repelled by magnets, you feel no effects like at all in your body when you're in the magnetic field?
Yeah, that's
Me-
correct.
Yeah, I feel nothing. If you can hear me, can you
Yeah,
hear
we
me?
can hear you. Yeah.
So I feel nothing being right here. And it is a bit surprising considering the things I'm holding feel quite a lot, you know. But no, I think what would make me feel something, and I don't want this to happen, but it would be if this field of this strength were to change polarity very quickly, which that's not what our magnet does. But when you have a changing magnetic field, that's when you can really start to influence things that aren't typically magnetic. So if this strong field started to oscillate, maybe I would feel something then, but not as a static field, not as I just stand here and hang out.
Yeah, I would just like to say some words about the numbers. What Derek feels now is not more than 100 millitesla. At that point, the magnet inside runs at 2 Tesla, that inaccessible point. That we are going to ramp up to 3.8 on Monday. And just for comparison, the medical MRI machines that are quite common everywhere in every hospital, they work up to 3 Teslas. And even the research MRI machines can go up to much higher, but they are very, very rare. The human body, as far as I learned, the human body will not feel any biological consequences up to 10 Tesla. But, yeah, Derek is really far from feeling anything.
Yeah. So in other words, at high enough magnetic fields, there will be an effect on humans, but we're still quite a bit away from that. And I did want to mention a few things. So we talked about magnets, and I still give you a sense of context here. So the technology for superconducting magnets is at this point in time, again, we can produce much higher fields, right? So the CMS magnet, by comparison, only can produce a fraction of an experimental magnet, for example, that can go up to, I think, if approaching 15 Tesla is about as much as we can do, I think. However, these are much smaller magnets. So what's interesting about the CMS magnet is that it has a lot of current flowing through it. So we're talking about 18,000 amperes in current, and it's producing that magnetic field across a very large volume. So that means it stores a lot of energy. And I don't remember, but I think it's on the order of 2 gigajoules, 2.6 gigajoules, but I would... So it's a lot of energy. It's like enough to melt hundreds of tons of steel. And it only will be surpassed once the ITER fusion experiment starts operation. So they're building those magnets now, but at the moment it's the magnet with the most amount of energy stored in the world. Okay, there's a couple of questions, so maybe we can take one of these one at a time. So what kind of materials are used to block the radioactive effects of the accelerator?
Concrete.
Yeah, so concrete shielding is the most obvious example.
That's a heavy concrete indeed.
Yeah. I think this is not common so much anymore, but you also sometimes will have lead blocks that are part of some shielding in some areas, but I think that's, again, not so common anymore. But that's a short and brief answer. Yeah, maybe let's take another question. So radiation is not fully contained within the cylindrical vacuum. You cannot really, so ionizing radiation is where you have particles. I mean, this type of radiation is very difficult to shield against. It also depends on the type of radiation, right? So it's sometimes water can be a very efficient shielding for radiation, and that is used sometimes. But in the case of our detector, the point is that we don't want to shield. So the innermost part of our detector is trying to do the opposite. We want to see that radiation. We want to investigate the particles that are produced in the aftermath of these collisions. So we don't. We actually the innermost part of our detector is designed in such a way that it doesn't have has as little impact. It is as little as possible an impediment to the movement of these particles, right? So you want your innermost detectors to be transparent in a way that you don't want them to scatter the particles that are being produced. Whereas the calorimeters, quite the opposite. There you want really dense material such that you can absorb the energy of the particles. And just to give an example, I mentioned this calorimeter, what we call the crystal calorimeter, the one that has to run at exactly 20 degrees. So that's using a type of crystals that we grow, and they contain like 85% lead and then also tungsten. So that's the scintillating material that produces light, but it is mostly lead. So it's a very, very dense material, and that's how you basically stop these particles. They shower inside this material. So that's hopefully giving you an idea. And then how much water is necessary to cool the electronics. And so if we talk about the electromagnetic calorimeter that I was just discussing, my recollection is, I mean, I don't know what this is going to mean to you guys, but in Geneva, we have the tallest water fountain in the world. It's called the Jet d'Eau, the water jet. And I think it's something like 100 meters tall. I don't remember exactly. Let's say 300 feet, something like that. And we use about a third of the flow of water just for cooling that electromagnetic calorimeter. Other detectors use different coolant. So the inner detectors, the innermost part of our detectors using CO2 as a coolant, and that we're expanding that cooling systems because we didn't talk once about the upgrade, which is a bit of a shame that we don't have much more time, but you did hear about it during the previous talks. But we need to replace the innermost detectors entirely, and also the forward calorimeters, and this will use CO2 as a coolant. So this for the upgrade, we will have a significant, I don't know the total amount of flow of CO2, but it is quite significant once we have the new inner detector and forward calorimeters. Okay, I think
we have to got some parents waiting outside, maybe in the cold Chicago weather. But thanks so much for sharing all this with us. It's really cool to see from the control room to the scale of the machine. Let's thank them all.
Of course.
For taking time on a Saturday evening. Where you all at? But yeah, thanks so much for taking the time, and we really appreciate it. And yeah, hope to talk to you all again soon.
Great. Thanks for joining us. See you.
Thank you.
See you.
Nice day, ciao.
Thank you all so very much.
Cheers.